All right, continuing on with factoring. This is 7.7, and today we're going to look at some special products. And we have done these special products when we had multiplying polynomials. This is really going to be about recognition because all of these can be factored the way we've been factoring them. But you are going to have to recognize certain situations that will make your life much easier. And the first thing we are going to talk about is the difference of two squares. Meaning I've got a binomial here where my A term or my first term is squared, and then I just have one other term, and that is squared. And if I remember back to multiplying polynomials, when I had two binomials that I multiplied together and my middle term went away, it was the product of a sum and difference, meaning I have the square root of A, or A, plus the square root of B. I have that. Because if I FOIL this back out, it would be A times A, which is A squared. Then I have minus AB plus AB. That would go away, and then B times a negative B is negative B squared. When you are factoring these, you are just going to take the square root of the first term and the square root of the second term. It will be a sum and a difference, and it will factor just like this. The key is going to be to recognize when you have two terms here, are A and B perfect squares? Are they numbers or variables that I can take the square root of? So if I have something like this, x squared subtract 9, I don't have a middle term, I'm asked to factor or solve, I recognize that this value right here, this is 1x squared, that's a perfect square. X times x gives me x squared. 9 is a perfect square. 3 times 3 gives me 9. You can take the square root of both of these numbers because they are perfect squares, and it gives me x plus 3 times x minus 3. Let's look at some more examples. 4x squared minus 1. Again, you had a two-term. It's not a trinomial, it's a binomial. And there's subtraction in the middle. Look to see, is that a perfect square? And is that a perfect square? I certainly can take the square root of 4. I can take the square root of x. The square root of 1 is 1. This is the difference of two squares, and it factors into a sum and a difference. You know, 1 is going to be plus, 1 is going to be minus. The square root of 4x squared is 2x. The square root of 1 is 1. And I have 2x plus 1 times 2x minus 1. Try that one real quick. One x squared, I can certainly take the square root of that. 25 is a perfect square. It is going to factor into a sum and a difference. One is going to be addition. One is going to be subtraction. I'm going to have the same terms in both binomials. Square root of x squared is x. Square root of 25 is 5. And it factors just like that into x plus 5x minus 5. Can rearrange the order on here, and it doesn't make any bit of difference. What I need to recognize is that I have a binomial with subtraction in between that is the difference of two squares, the difference of two perfect squares. The square root of 100 is 10. The square root of m squared is m. This factors into a sum and difference. You know you're going to have the same terms. One is going to be addition, one is going to be subtraction. The square root of 100 is 10. The square root of m squared is m, and it is 10 plus m times 10 minus m. You could also certainly rearrange this. I could make this negative m squared plus 100. I could factor out that negative, make it at m squared minus 100, and you'll certainly still get the difference of two squares there. The order would just change, m plus 10 and subtract 10, and I still have it. This is the same as that, because if I make that negative and distribute that negative, it's going to switch everything around. This would be this one would be that one. And we can also use this, like we did these special patterns, to do some mental math without using a calculator, using just the pattern. 54 squared minus 48 squared. Sum and difference is very helpful with this. This is the difference of two perfect squares. This is just like what we have up here. This would factor into a sum and a difference. This would factor in to 54 plus 48 times 54 minus 48. And then I can just do the math following PEMDAS. 54 plus 48, that would give me 102. 54 minus 48 would give me 6, and I can mentally even do that. 6 times 102, 6 times 100 would be 600. 2 times 6 is 12. 600 plus 12 is 612. So there'll be some problems coming your guys' way where you'll recognize the difference of two squares. We're going to write it out, and we are mentally going to do that math to get it. Yes, I am perfectly aware you can just put that into your calculator to get it, but we're going to practice these doing pattern recognition. That is the difference of two squares. The next thing we are going to look at are perfect square trinomials. In perfect square trinomials, if we remember back, if I had something like this, this was back from multiplying polynomials. Going back to what we did when we were foiling, I gave you lots of these to multiply, and it was the squared. Remember, this is a plus b times a plus b, and remember, we took the first term and we squared it. I took a times b and then I doubled it, and then I squared my last term and I had it. We're just going to be working backwards. So we are going to recognize, is my a value a perfect square? And is my b value a perfect square? And if it is, and I get the middle term as double the product of a and b, that's the way it's going to factor. The same thing is going to hold true when I have subtraction. And if we remember doing this as well, if I have a squared minus 2ab plus b squared, everything was the same except my middle term, or my sign in my binomial, was subtraction. Because I would take my first term and square it. A times negative b is a negative ab, and I would double it because I have two of them. And then negative b times negative b is b squared. So the key is going to be recognition. Here's the first example. N squared plus 8n plus 16. Hopefully you recognize right now, say, hey, Mr. DeLong, the coefficient in front of my squared term is a 1. This might factor. So I could also look at this and say, you know what? I need factors of 16 that give me a sum in 8. Well, I know it's 4 and 4. So this would be n plus 4 times n plus 4, and I can write that, and we will have to, I want you to write these like that. I don't want this written like n plus 4 times n plus 4. We want to write it like that. Pretty easy to recognize when that coefficient of 1, where it kind of breaks down is when I give you something like this, and here's where the recognition part comes in. 4x squared minus 12x plus 9. Here's where I want to start thinking. If you just go into this blindly, you would just get factors of 4 and factors of 9, right? 1x, 4x, 2x, 2x, and I would have 1 and 9 and 3 and 3. And I would say, hey, this is positive. I know I have a sum. I'm looking for factors of 9, some sort of combination that's going to give me a sum of negative 12. I know both signs are going to be negative. And I can see right now that it's going to be that right there. 2x times 3 is 6x, 2x times 3 is 6x. I add them together and I get negative 12x. So it would be 2x minus 3 times 2x minus 3, or 2x minus 3 squared. What I want you to recognize is when you have something like this, it certainly may factor into this. I try to recognize, is my a term, my first term here a perfect square? Is my last term a perfect square? Are they numbers I can take the square root of? Yes, they are. There's subtraction in the middle. I'm going to try this. 2x minus 3 squared. It is not always going to give you that middle term of negative 12. For the most part, with what we do, it is. But as you move forward and these get a little more complicated, I need to double check and make sure that I can take my a times b and double it and get that value. 2x times negative 3 is negative 6, and if I double it, it's negative 12. So this does work. It is much easier to recognize that this is a perfect square trinomial and factor it this way than going through all of this. Because as these numbers increase, if you don't recognize them as perfect squares, the combinations that you're going to get are going to be many. And then you're going to have, then when you get down and figure it out, oh my goodness, I got the exact same terms. That was a perfect square trinomial and I didn't even recognize it. So let's look at this example here, and we're going to show you how this factoring completely comes in. 9z squared plus 36z plus 36. First thing we should look for, always, can you factor something out? I can. 36 is divisible by 9. I can factor out a 9, and that's going to make my life much easier. That would leave me with z squared plus 4z plus 4. I can recognize right here, this is a perfect square trinomial. This is a perfect square trinomial as well, and we're going to get to that in a second. I just want you guys to get in the habit of always taking out a greatest common monomial first, because it may make this way easier to factor. Now this one, even if I didn't recognize it, factors of 4 that add to 4, I know it's going to be 2 and 2. This is 9 times x plus 2 times x plus 2, or it is going to give me 9 times x plus 2 squared. You could also recognize that this is a perfect square as well. Nine, I can take the square root of. 36, I can. Now, if we're looking to solve, we'll go over that. If I recognize that's a square and that's a perfect square, it's all addition. I'm going to try it. It might be 3z plus 6 squared, because if I take the square root of 9z squared, it's 3z. Square root of 36 is 6. It's all addition. It's going to be plus. I am going to look at this. And FOIL it out to see if I get 36. 3z times 6 would be 18. I double it. It is 36. This, however, is not factored completely. I could certainly take out this 3 here, which makes this 3 times z plus 6 squared. I'm sorry, not 6. Three goes into 6 2 times, and I have that. And I can see if I used zero product property, set both of these equal to 0, my solution is just going to be -2 for both of them, no matter how I got there. Even if I got here and was asked to solve, and I set that up, I would subtract 6. 3z is equal to -6. I would divide by 3. X is equal to -2. And it's going to give me the same solution. This is factored completely, and so is this. What do I mean by factored completely? Meaning what's inside my parenthesis here, my binomials, is simplified all the way down. No number have in common here except 1. Here they had the 3 in common. You can certainly solve from here and get the answer, but if it says factor completely, we need it totally reduced. We're going to get into some solving. And you're going to have some with some fractions. But again, it is going to be recognition. I'm going to look right here. That's a 1. I would look factors. What multiplies to give me a 9th and adds to 2/3. Might have to think through that a little bit, especially if we aren't comfortable with fractions. But what I can do is see if this is a perfect square trinomial. I can take the square root of 1x squared, and I can certainly take the square root of 1/9. Square root of 1/9 is 1/3. This may be x plus 1/3 quantity squared is equal to 0. X times x is x squared. 1/3 times x is 1/3 x, and I would double it, and if I got 2 of the 1/3 x's and I add them together, that gives me 2/3 x. 1/3 times 1/3 gives me 1/9. I don't have to solve this twice, but it is this, remember. This is what we're going to get back to our repeated roots. I don't have to go through and solve this 2 times. I'm going to get the same thing. I know that x has to be -1/3. And yes, I only get it 1 time. I don't have to do this. I don't have to write -1/3, -1/3. It's -1/3. What comes in really handy as well when we have these perfect square trinomials is solving them. Because remember, I can solve, if I factor this right here and I'm left, I'm going to take this and rewrite it right there. If I have x plus 1/3 squared, and that's equal to 0, and I want to solve this to get rid of something squared, I take the square root of both sides. That gets rid of my squared. That leaves me with x plus 1/3 is equal to the square root of 0. Well, the square root of 0 is just 0. Now I can subtract 1/3. X is equal to negative 1/3, and I still get the answer. I want to show you something else that works as well, especially with fractions, and I like to do this. I'm going to start with what we had. X squared plus 2/3 x plus 1/9 is equal to 0. Sometimes it's easier if I just clear these fractions. And to clear the fractions, I would want to multiply this whole equation by 9. Why would I use 9? Because 3 goes into 9, 9 goes into 9, it will clear these fractions. If I choose to do so, I can multiply by 9 and just distribute 9x squared. Well, if I do 2/3 times 9, 3 goes into 9 3 times. That gives me plus 6x, and then I take 1/9 times 9. That's plus 1. And now, this is a lot easier to recognize as a perfect square trinomial because I have integers there. I can take the square root of 9, and I can take the square root of 1. This gives me 3x plus 1 quantity squared equals 0. I know that that is 3x plus 1 times 3x plus 1. I certainly don't have to do it twice because I'm going to have a repeated root because it's squared. I could subtract 1. 3x is equal to negative 1. I divide by 3. X is equal to a negative 1/3. And I got the exact same thing I did over here, just going about it a different way. I could also be left with what I have right here, which is 3x plus 1 is equal to 0, and that 3x plus 1 is squared. And I would solve it the exact same way I did over here. I could take the square root of both sides, which leaves me with 3x plus 1 is equal to the square root of 0, which is 0. And now I'm right back to this equation right here, which I just solved. I would subtract 1 and divide by 3, and I still get negative 1/3. So a whole bunch of different ways to get to the same solution. The key is going to be you will save yourself time by recognizing these are perfect square trinomials. If you don't, and you're on the assessment or the test or on your homework, these are going to take much longer. And what happens is on the test, we don't recognize them, and then we get big numbers here that we don't recognize as perfect squares, and we spend too much time factoring if we can even get it to factor, and we just burned up a bunch of our clock. Recognition is the key. One other thing I want to mention is back to what we talked about when we were using exponents about our solutions. Remember, if you have something squared or an even power, if I have something like this that is x squared is equal to 4, and I wanted to solve it, I would take the square root of both sides. X is equal to, I have two potential answers, plus or minus 2. Because negative 2 times negative 2 gives me 4, and positive 2 times positive 2 gives me 4. Now up here it doesn't really matter because it's equal to 0, and I take the square root of 0. It's not plus or minus 0, it's just 0.